Welcome to section 11.3. We are almost done. The tangent line problem. So if you're going into calculus, this is going to be super important concept. Notes here are going to be pretty short, but the examples are super long. I haven't made that video yet, but I'm guessing they're going to be super long because these problems are super, super, super involved. But I'll let you know, a question like what we are going to do in this section is material that actually shows up on the AP Calc exam, and usually more than once. You're looking at maybe 2 or 3 questions on the AP Calc exam that are just what you're learning right now, right here in pre-calc with nothing additional added to it. So that's sort of cool. We're going to jump right in. We'll get some definitions and fun stuff. So in this section, we're going to be using limits that we learned in previous sections to develop the idea of a slope of a tangent line to a curve. So that's really what we're going to be talking about. So to talk about a tangent line is a line that approximates the slope of a curve at any particular point. So like, to explain a little bit here, something that you guys are used to is looking at like this linear function. And if I said that this linear function, f of x, is equal to 2x plus 3, you would say that m here is 2, which is the slope. But what if that function isn't linear? When we talk about that, the slope at any given point is different. Right here I had some positive slope. Right here I have a slope of 0. Right here it starts going down, so I have a negative slope. A tangent line at the given point is a way of approximating the slope at that particular point. So here, if I'm looking at like this point x2 comma y2, this tangent line, I'm going to hyper zoom real quick. This tangent line here is a way of approximating the slope at exactly that point. Here, this tangent line is a way of approximating the slope at exactly that point. And that's what we're talking about when we're talking about this tangent line. So the slope of the tangent line can be used to approximate the rate of change of the graph at a particular point. So just some other things here. To approximate the rate of change, which is the slope of the graph, meaning the function, at any, particular point. So if I wanted to know, I'm looking at some cubic function, and it's like, yeah, sometimes the slope is positive, sometimes it's negative, then it goes back to being positive because this is increasing, then decreasing, then increasing. But if I want to know about the slope right here, what I do is I calculate the slope of the, oh, Jesus, that was really bad. I calculate the slope of a line that is tangent. That was also bad, but I can at least fix that one. So I take this tangent line, if it lets me take it, which it's not. There we go. Come on. Okay, fine. I'll do it like this. So I take this tangent line and I use that slope to approximate the slope right at that point. Okay, so graphically, that's just a little bit of an explanation. But now, like, how are we actually going to do that? But think about how we have always found slope. We've always found slope by doing the change in your y value divided by the change in your x value. So m is equal to y2 minus y1 over x2 minus x1. This is the slope formula as you have always learned it. That's also equal to then delta y, this delta, oh, sorry, wrong tool there. This delta, meaning change. So it's the change in your y value over the change in your x value. This is how I can find the slope between 2 points, x1, y1, and x2, y2. But what if I want to find the slope at a single point? Well, the problem, if I was trying to find it at a single point, is that I would have the same y value, I'd have no change in y, over no change in x. So my rise would be 0 and my run would be 0, which is indeterminate. And again, just sort of think about that. If I said I'm at 1, 2, and I wanted to know the slope between these 2 points, but let's say I didn't know what this point was. If I just wanted to use this point, you know, y2 minus y1, I'd have no change in my y value because I'd have 2 minus 2 over 1 minus 1, since those are my x values. When I do that with a separate point, I'm able to find the slope. Okay, so what that is going to take us into then is sort of a little bit more complex. So try and follow along. What we're going to do is find the slope of a secant line. So secant lines, if you remember back to geometry, that means that they intersect the curve at 2 points. So the 2 points that I'm going to use here are going to be x comma f of x. So that's right here, x comma f of x, where this is just saying some x value and the y value that you get at that x value. Then, here's x on my x-axis. I'm going to move over h units. That was not a very good h units. So if I'm talking about what this point is, this is the point x plus whatever h was. And if I wanted to talk about this point then that's on the function, it would be x plus h, because that's whatever x value I'm at now, comma, f of x plus h, because that's just going to mean the y value at x plus h. So if I wanted to use my slope formula, you remember that my slope formula is y2 minus y1 over x2 minus x1. So I would have y2 f of x plus h minus f of x over x plus h minus x. You could see that that cancels then. And what I'm left with is f of x plus h minus f of x over h. Well, that should look pretty familiar because that's what we've already been doing. That's the difference quotient. So now that gives us the slope of any line that's just going between 2 points. What we want to do is take this point, and I'm just going to make it a different color for emphasis reasons. I want to take that point. So here I'm starting at f or x comma f of x, and I want to make this point, I want to take this point and move it closer and closer and closer and closer and closer and closer and closer towards the original point. Because what is that doing to my tangent line? Well, that's taking my tangent line and it would lower in that same way until eventually I would be getting, it's a little bit tougher to do. Sorry, that was a secant line. I'd be getting a secant line that's going to get closer and closer and closer and closer to the tangent line at this point. So I'm just going to sort of re-demonstrate that. Follow along with me. I don't know how to move that blue line. Come here, blue line. Oh, okay. Well, that blue line is just going to hang out there. Let's say that this wonderful blue line is my tangent line. So this blue line is my tangent at x comma f of x. It's only hitting it at 1 point. what will now become a red line, my red line, which is the secant between these 2 points. As I move this point, oh, it's not letting me do that. We can do this, don't worry. So again, my red line is the secant between these 2 points. As I move this point closer and closer and closer to x, this red line is going to get more and more and more near to the blue line. They'll essentially start becoming the same line. Well, what does that mean about my h value? Over here, h was, something like 7. And then as I'm moving this closer, I'm making it 6, and then 5, and then 4, and then 3. So what I'm trying to do is make h 0. So I'm shifting that h closer and closer and closer and closer to 0 so that I can get a line that's essentially the tangent line. So as I move these points closer, what I'm doing is taking the limit as h goes to 0 of f of x plus h minus f of x over h. So essentially, I'm taking that distance between these 2 points and making it infinitely closer together so that I can calculate that slope. And what this finds is the slope of the tangent line at x. So right here, what this is the slope of the tangent line at x. But if you remember from section 11.2, this is also the derivative. So when we talk about a derivative, one way that we can come up with that is the slope of the tangent line at x. This would be the derivative at x. All right, so we're going to do one example here live. Find the slope of the tangent line to f of x at specifically 2, 5. So I'm looking for the derivative at a specific point. So first, I need to do the difference quotient. So this will become the limit as h approaches 0 of x plus h squared plus 1 minus x squared plus 1 all over h. Now this is, all I'm going to do is pretty much an 11.2 problem for right now. So this becomes the limit as h approaches 0 of x squared plus 2xh plus h squared plus 1 minus x squared minus 1 all over h. So my x squareds cancel, my minus 1s cancel, and I can factor out an h from the top of this. So I get h, 2x plus h over h. And now, if I take the limit as h goes to 0 of 2x plus h, I get 2x. So this is the derivative, or the slope of the tangent line, slope. But what I want is the slope of the tangent line at 2, 5. So now I have f prime of x, and we will talk about what this means. F prime of x is equal to 2x, and I want f prime of the x value here, 2, which would be 2 times 2. So f prime of 2 is equal to 4. What is this telling me? The slope of f at 2 is 4. Graphically, x squared plus 1, we're talking about a parabola right here. What we just came up with is what the exact slope is at the y value, or sorry, at the x value of 2. So I know that the slope right there is 4. It's a pretty cool thing, because before the only way that you knew to come up with slope was of linear functions. Now I can get the slope at any given point of pretty much any function. Riveting. All right, more examples that we'll do in the examples video. Those take a long time. Now all I want to talk about is, what does that mean? Okay, cool, a derivative of a function. The derivative is the formula for the slope of the tangent line at any given point. So it is a function of x. That is super important to realize. When we're talking about the derivative, we're talking about a function. So f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And the derivative is read as f prime, that symbol meaning prime, of x. Some other stuff to keep in mind is that the derivative is a function. To find the slope, which is the rate of change, of any given function at any given point. So when I talk about the derivative function, it's a function that can be used to get the slopes. So instead of getting the y value on my graph, I'm getting the slope at that point. Sort of interesting. So continue on. Definitely go maybe daddle a little bit with those examples, because they're pretty good, and as I said, they're pretty extensive. So you might want to hear just a few of them, maybe 1, 2, or all of them. I'm not going to hold you back, but there is a lot that goes into a lot of those questions. I'm just going to warn, they're pretty long questions, so you're going to have to bear with me. Maybe pause the video here and there.